Thank you, Charles. So, this morning I'm going to discuss some microwave multi-photon phenomena. And a lot of this work has been done with many other people, starting with Pierre Piet, Ben Gendron, Kevin Russell, Stoneman, Louis Bloomfield, Duncan Tate, my present colleague Bob Jones, Joshua Berger, Veruca Maeda, Don Doram, Richard Overstreet, and Alexander Heraklion, who's here. We'll be happy to answer any questions. So what I'm going to do is to briefly introduce why you might want to do this, partially by talking about multi-photon ionization and microwave ionization. And then we will wander from that into how you think about microwave fields as time-varying fields or things that drive transitions and how you can put those two together, which is a concept that actually can be useful even in things like dipole-dipole interactions. And then I will go on to how you can use microwaves to manipulate states, building on some of the things we've learned here. And this will be sort of the low-end version of what Barry Dunning talked about yesterday, but from a rather different point of view. And finally, if I don't talk too slowly, we'll go back to revisit microwave ionization and multi-photon ionization. Okay, so as Peter Spelter just pointed out moments ago, it takes enormously strong fields to ionize ground state atoms. And it's easy to compute the classical field for ionization if you just consider the energy level. An atom that's bound by an energy of 1 over 2n squared. I erased all of my slides last night, so I had to start over. I forgot a few things. Anyway, the field is easy to work out. Is a field of 1 over 16 n to the 4th in atomic units, if I neglect the stark shift of the level. And so for n equal 20, that's 2 kilovolts per centimeter, which is a reasonable field. For the ground state, it's 5 gigavolts per centimeter, which is not a field that you're going to produce between a pair of capacitance plates. Now, so if I could go back to thinking about the ground state, even though I'm obviously not going to field ionize it directly, probably. If I put it in a field, as I've just said, I will in fact actually have to apply a field that's 1 over 16 n to the 4th, and it will ionize by just pushing down the potential on one side. On the other hand, if I considered applying an AC field to this, in the limit of high frequency, if the photon energy exceeds the ionization limit, then I can ionize the atom. Okay. And halfway between these two is multi-photon ionization, in which case n times the number of photons that you have to absorb has to be over the limit, and you need high intensity because it is an n photon process. So if you in fact look at the early calculations of this, the logarithm of the ionization signal was often plotted versus the log of the laser intensity used to do this, and of course the likelihood of ionization went up as the intensity to the nth power, where n is how many photons you have to absorb. Okay. This, of course, is the lowest order perturbation theory result. Now, a slightly different way of plotting that would just be to plot it on a linear scale, which is the ionization signal, of course, looks like the nth power of the intensity. It's almost flat, and then it goes up where the intensity in some scaled units, I over some I0 becomes 1. Right? So, in a sense, the interesting question is, why is it at this field, right? It's the fact that it's going up like this, you know from perturbation theory. So the physics in some ways is, what's this field? Now, of course, since you have to have high intensities, if you want to multi-photon ionize the ground state, you have to use a laser, a pulse laser, and you have to focus it. And so, the laser field is by definition inhomogeneous in space and time. So it's focused, and then it's a pulse. And if you're trying to look at a nonlinear process with something that's inhomogeneous in space and time, this is kind of hard. So if you realize that the atom field interaction is mu e, right, it's the product of these two, in the laser experiments you make the field big, and the dipole moment is small. It's usually something like 1 atomic unit. And so in a Rydberg atom, you can have enormous dipoles, and so you can make the field smaller. But of course, since the Rydberg binding energies are small, if you want to do multi-photon ionization, for example, you have to use a pretty low frequency, so we use microwaves. Now that, of course, has an additional advantage, which is that microwaves often have, say, at 30 gigahertz, have a wavelength of 1 centimeter, and you can make small samples of atoms compared to that, so you can easily do experiments in which all the atoms see the same field. And it could be basically a CW field, or it could be pulse. You don't have a situation where the atoms over here on the edge of the laser beam see practically no field, while the ones in the center see a gigantic field. So that's, in fact, the attraction of doing this. So you could, in fact, imagine addressing the following question with the linearly polarized microwave field. Can I connect field ionization to multi-photon ionization to photoionization? I mean, how do I connect these apparently different descriptions? And so a way that you can think of doing this would be to do microwave ionization at 10 gigahertz. If you, in fact, look at states above n equals 600, you, in fact, can photoionize them. They're bound by less than 10 gigahertz. At n equal 85, the spacing between the levels is 10 gigahertz. At n equals 70, the spacing between the levels is 2 gigahertz. So here it would be a 2-photon transition, here 1. And of course, at much lower ends, it takes lots of microwave photons to go between the levels. Now, the first person to think of this was actually Jim Bayfield. And so he and his student Peter Koch reported the first microwave ionization experiments with hydrogen. And the idea of the experiment was to pass a beam of n equals 65 atoms through microwave or RF cavities and measure how many atoms survive as a function of the field strength, okay, to determine the ionization fields. And what they saw is shown here. So this is, in fact, their slide. It's plotted in terms of the Keldysh parameter, and they used, in fact, 3 fields, 30 megahertz, which they call DC, 1.5 gigahertz, and 9 gigahertz. So 9 gigahertz is a little bit less than the Kepler frequency at n equals 65. So if you convert these probabilities from a scale that uses the Keldysh parameter to one that just uses the microwave field amplitude, you find that the half points of these occur at 1 over 9 into the field that corresponds to 1 over 9 into the 4th for 30 megahertz and 1.5 gigahertz, but it's a little less for 9.9 gigahertz. Well, here I've used n equals 65. N is 65. Okay, so these two sound sort of like field ionization, except of course it has the wrong prefect, the astute observer. And this one is a little bit less. Of course, you would expect this to be a little bit less because you're coming close to the resonant frequency in the atom. Okay, well, actually it turns out that the 1 over 9 into the 4th is actually like classical field ionization. So when I arrived at this classical field ionization, I said there's no Stark shift. So if I consider an atom at this energy, this line, by the way, is the classical field ionization limit. This is 1 over 16 into the 4th. So I would compute, if I used n equal 8, I would get this field. However, if I take into account the Stark shift of this red n equal 9 state, it actually comes down to this point. So if I take into account the Stark shift of a red state, actually this 1 over 9 into the 16 into the 4th with no Stark shift becomes this. So this is actually the field at which the red state of hydrogen ionizes classically. Now, these lines, of course, go out further for the blue states than the red states. They terminate where the ionization rate is something like 10 to the 7th per second. Okay, this, of course, is completely counterintuitive. Why are red states less stable than blue states? They have lower energy. Well, the reason is that in the red state, the electron is by the saddle point in the potential. In the blue state, it's on the other side of the atom, and there's something like, roughly analogous to a centrifugal potential that keeps the electron in these blue states away from the saddle point. So it's just not in the right place to ionize. So what they in fact see is simply field ionization at the end state they started with. Now, okay, I have to be a little bit more careful in this. the microwave field, say if I was in n equal 8, for example, sloshes back and forth like this. And actually it mixes up all of the n equal 8 states for the following reason. There is in fact a slight coupling between the n levels in the field, and so there's curvature to these levels. And because of that curvature, I mix up these different n equal 8 states that I've just drawn the extreme states here. And some of them come into the red state. If you come into the red state, you then of course bring the electron out to the saddle point and it ionizes. So this is basically the leak through which all the atoms in one state of the same principal quantum number ionize. Okay, so in hydrogen it's just simple field ionization, basically. There's nothing complicated about it. Okay, so about a decade later, thought it would be interesting to try microwave ionization of sodium. Field ionization of sodium is completely different. And since we, at that time, always liked to operate with relatively low line states, we were using 15 gigahertz, which for reasons I'll come back to in a second. And we started around n equal 20, where the spacing between the levels is 800 gigahertz, 27 wave numbers, or it's about 50 photons, 50 of our photons. 15 gigahertz is half the photon. Okay. So the way that we did this experiment is shown here. You excite the atom with a laser, you apply a microwave pulse and see if they ionize. So here's the pulse laser, the microwave pulse. And then we applied a field pulse, and the field ionization signal came out slightly ahead of the microwave ionization signal. And I used the same apparatus that was I showed yesterday. In fact, we built this apparatus to study these dipole-dipole collisions in the microwave field. And we thought, well, let's see what happens if you just put one atom in the field. Okay. So what you see, these are oscilloscope traces. When you populate the 23S state with no microwaves, this is a field ionization signal. Turn it up to 230 volts per centimeter, nothing changes. At 290 volts per centimeter, you start to see something later. And at 408, it's all later. So the ions come out later because they're pushed out by the rising edge of that field pulse, whereas the atoms only start to move after they field ionize and the pulse is bigger. But the bottom line, though, is, and since I think I recorded these traces, basically the atoms are either in the state we put them in or they're ionized. And so here's an example. If you look at the field ionization signal for 20S, it drops, and the microwave ionization signal is exactly its complement. So we detected the ions in both of these cases. Okay, so if you go on to do this, it turns out that if you polarize the lasers perpendicular to the microwave field and you excite D states, you can make the M equal 2 states. And they ionize out here, and they in fact ionize at the same fields that hydrogen does. Basically, this is just field ionization. On the other hand, the M equals 0 and 1 states have completely the wrong dependence. They have a 1/3, well, they're close to the line that's 1/3 and to the 5th, which was a little puzzling at first. But in fact, what is 1/3 and to the 5th? Well, that's what's sometimes called the Inglis-Teller field. It's the field at which the extreme Stark states in hydrogen actually run into each other. The extreme Stark states have shifts of 3n squared e over 2. Spacing is 1/n cubed. So the field at which they cross here is 1/3 and to the 5th. This drawing is actually for hydrogen, and these levels actually cross in hydrogen for the reason that Peter Schmelzer just gave. There's a symmetry that's there, and hydrogen the electron sees a point nucleus. In sodium, that's not true. If you look at the M equals 0 or 1 states of sodium, they in fact have the S and P states with big quantum defects, which means that the electron is sensitive to the fact that the core is not point. And so there are avoided level crossings between these states that come up from, say, n equal 15 and the ones that come down from n equal 16. And in fact, due to these avoided level crossings, as the microwave field comes out and hits here, you in fact can have slightly non-adiabatic transitions and make transitions into the upper state. I think just for the sake of argument, I will just remind you of the criterion for this. So we often speak of these as Landau-Zener transitions, which is how people in condensed matter physics discuss these, or in collision physics. And if I have two levels shown here by the broken lines, which have no coupling, they cross like this. On the other hand, if there's something that couples the two of them together, you in fact have an avoided crossing, which is proportional to the magnitude of the coupling. I mean, at degeneracy, that's all there is. If, in fact, the levels change as a function of some parameter, in the case I just showed you, it's an electric field. It doesn't have to be an electric field. If I, in fact, slew this electric field so that the energy spacing between these two levels, the unperturbed levels, that is, as long as that slew rate is much smaller than the square of this spacing at the avoided crossing, the traversal is exact. That is, I'll follow this bold line. And I will, in fact, go from one of these sort of uncoupled states to the other. On the other hand, if the slew rate is really fast compared to the avoided crossing, I just follow the dotted lines. Okay. So that, we'll use this again later, but anyway. So our contention is that basically what we're seeing is that the atoms are going out here, and they're going through these, through this avoided crossing partially diabatically. It's clear if it's either purely adiabatic or purely diabatic, nothing happens. Okay. So then, of course, the way that this ionizes, if you start at n equal 20, and the field is big enough to reach the anti-crossing with 21, you can go up to 21, but it's not big enough to reach the field down to 19. Okay, so once you've gotten to this one, you clearly have enough field to get here, and you just sort of zipper your way on up and ionize. Okay, so well, actually, if you're paying attention, you realize that if you look at these data, you realize there is a small problem here. Namely, this is the line for, this is 1 over 3 into the fifth, 0.33 times into the fifth. And our data are actually at something like 0.28. So the field doesn't quite get to the avoided crossing. And so how exactly is this going to happen? So I will, in fact, try to convince you that these transitions from n to n plus 1 are actually resonant multi-photon transitions. And I will attempt to show you how you can think of these as coherent multi-cycle Landau-Zener transitions. Okay, so the micro-ionization problem is kind of a mess. I mean, there are too many, the detector is too far removed from the rate limiting step, which is that n to n plus 1 transition. So it would be nice to have an analogous problem where you can just look at it. Okay? And so we decided, let's look at an isolated avoided level crossing that has the same physics. So in the potassium atom, it turns out that the S state, the NS quantum defects are 2.3, and the S states are quite close to the high L states. And so the 18S state has almost no Stark shift, and it comes out here, and it intersects the lowest Stark state of n equals 16. Now, there's an avoided crossing here due to the core coupling, exactly like the ones I showed you in sodium a minute ago. Okay. So in principle, we should be able to, in fact, look at transitions from this S state up to this Stark state and see if we can understand it any better. Okay. So the first experiment to do, of course, is then to just excite, let's say, the atoms to 18S in zero field with the pulse laser, put on the microwave field, vary the amplitude of the microwave field, and look for population to show up here. You expect that when the amplitude of the field gets out to here, you'll see it, right? At least that's what we saw in the previous case. And in fact, that is in fact what you see. So this is the field of the avoided crossing between 18S and the lowest Stark level of n equals 16. And okay, it works there. So it looks like this is the same problem. Okay. Now, but if we go up one end, to 19S, it intersects the n equals 17 states right here. And it wasn't quite what we expected. So here we have this big blob here, and then after that, you see it makes the transition. So later we realized that in fact these are due to multi-photon transitions from 19s up to this low-lying Stark state that are introduced by an AC power shift, which isn't big, but it's big enough. Now, so if you have multi-photon resonances, you ought to be able to see them directly. And so to explore that idea, you notice as you move, if you move along here in a static field now, okay, here one microwave photon will take you from one to the other. Here it's 2, 3, etc. So if you fix the microwave field at some frequency and some amplitude and sweep the static field, you ought to see a bunch of these transitions. Okay, so if you populate 18S and look for these transitions, in fact you do. So here we have, in fact, the spectrum that you observe for this transition as you scan the static tuning field. The level crossing of these two states without any microwaves is, I think, 753 volts per centimeter. So you can see this very clear picket of transitions. Each of these things is the field that corresponds to shifting the two levels one more microwave photon apart. And okay, I mean, it's completely obvious that this is, you have this picket fence, so you can see everything from 1 to 28 photons. Now, there's a little bit of extra junk in here and here. Those are transitions to the higher lying Stark states, but I'm going to ignore them. I mean, what I want you to concentrate on is the fact that you can see this regular picket fence that goes all the way out there. What you can't quite see here is, in fact, at high microwave powers, there are power shifts of these. That's what led to that early onset in the 19S curve a minute ago. Now, the other aspect of this that's really kind of interesting and surprising from a multi-photon point of view is the maximum number of photons you can see, that is, see the n photon transition, increases linearly with the microwave field. So with a microwave field of 100 volts per centimeter, I can see 10 photon transitions. With 200, I can see 20 photon transitions. Okay. This is completely different from standard multi-photon processes. Okay, so how do we understand this? And we're going to approach this two different ways. So first of all, I would like to just approach this as a classical resonance problem. And we're going to do this using a Floquet approach. And if you haven't ever looked into this, I would start with the paper written by Chirped. The basic idea is that the Floquet eigenstates are periodic, and they vary with the period of the perturbation. It doesn't have to be a sine wave, but it just has to be periodic. And so I want to consider an S and a P state. In the presence of this field of p omega t, or actually, I in fact can create the states that are the p state, s state plus a photon, or p minus a photon and s. And I can make a whole ladder of these states in which I add or subtract integral numbers of the microwave frequency to construct these Floquet states. All of these pairs are completely equivalent. It doesn't matter whether I look at this pair or this pair. So if I then draw the Floquet energies of my two states, say I've chosen P and the S state plus a photon, as I raise the frequency, of course, they come into resonance right here, where the microwave frequency matches the frequency of the transition. Now, the other thing I will point out, and I'll try to mention this several times, the Floquet energies are cycle averaged or time averaged energies. They're not instantaneous. They're averaged over one cycle. Okay, but so here these two states are degenerate at resonance. But if I in fact introduce the dipole coupling UE due to the oscillating field, I in fact lift that degeneracy, and I have my two states originally look like the dotted lines, and now they in fact look like they have an avoided level crossing with a separation which is twice this dipole matrix element. Okay. And in fact, the size of this level crossing is in fact the Rabi frequency. That's in fact the frequency in which atoms, if I put them into either the S state or the P state, that's the frequency at which they oscillate back and forth. It doesn't matter how I get this avoided crossing. If I have Floquet states, that between any two Floquet states, that avoided crossing is always the Rabi frequency. Okay, so now after that very brief introduction to Floquet theory, probably making all the theorists' eyes roll, but anyway. So now let's apply this to our problem. Okay. So we have two levels. One of them is coming down with this linear Stark shift, and one has no Stark shift. And so the upper state has a field that looks like this. So let's imagine I'm sitting at this static electric field. When I apply the microwave field, I'm doing this to it. So the microwave field is oscillating like this. And so the energy level is being modulated up and down. Okay? So those of you who are experimentalists know that if you modulate the energy, say, of a laser beam or a radio wave, you produce sidebands. Okay? And in fact, that's what happens in this case. The oscillating microwave field produces sidebands of this state. Okay? Okay. So you can make that notion a little bit more quantitative. Well, you can make it quite by writing the field in this fashion. And then, since this is in fact a Floquet problem, I assume that I in fact have this state in the presence of this total field is some spatial state with a time dependence. Okay, I can solve the Schrödinger equation to find this time dependence in the presence of this energy. And this is in fact what you get. So if I do this integral, and I find that I have e to the I times this energy minus its Stark shift, so let's say it's at this Stark field. Okay, this you know. And then I have this e to the I times this sinusoidal oscillation. This, however, can be expressed as a Bessel function. Okay? So when you do that, you get this. And if we put this back into the wave function, I recover sort of the initial wave function for this state. That's what it would be in the static field, multiplied by this Bessel function expansion. In other words, the original state has been replaced by the carrier, which is m equals 0, and a bunch of sideband states that have different amplitudes. So if you look into how Bessel functions work, you find that they have appreciable amplitude for the index equal to the, up to the point where the index is equal to the argument. And so the energy span is just m omega times ke. Okay? And that's why the number of transitions that you can see goes up linearly with the microwave field. It's just linearly proportional. Okay. All right, so, but pursuing this a little further, if I had no microwave field, the core coupling at this point was just B. Right? This is due to the fact that I have a finite sized core. So the nth sideband, so here's m equals minus 3, in fact has a coupling with this state, which is obtained by just taking the same core coupling between the sideband state and this state here, which is 2. And so it's the same as the original one, but it's multiplied by this Bessel function. Okay. So the Rabi frequency at any of these resonances is simply the original avoided crossing due to the core multiplied by this Bessel function. Okay. Or at least so I claim. Okay, but you can measure that, and this is actually correct if you, by exciting the atoms at these points, turning on a microwave field at different amplitudes and just measuring the beat frequency. So we've done that for several of these transitions, and here these aren't any more visible than Peter Smelter's. So when you make these measurements, you can in fact see, yes, you in fact do get the correct Bessel function expansion. Okay. Now, let's skip that one. All right, so if you were sitting here, you might be asking yourself, we started out on this by some Landau-Zener picture. What does that have to do with what I just told you, if anything, or is this just completely unrelated? Well, you could also solve this problem by just writing down the fact that I have these two states with this avoided crossing, and then put in the total field here and solve the Schrödinger equation and look for the transition probability from here to here. Okay? So if you do that, you actually get what looks like the Rabi line shape as a function of the tuning field. So okay, quantitatively, it's easy to do this. That, of course, doesn't explain in any physical way what the connection is. But the physical connection is actually shown here. Okay. So So let's assume that we pick a static field where it's M photon resonant between these two states. That means after one cycle of the microwave field, this state has advanced in phase by m times 2 pi compared to the lower state. Okay, so each time the microwave field comes out here close to this crossing, it samples the curvature of that crossing. And at that point, of course, it picks up a little bit of transition amplitude. Okay. So if you're tuned to the resonance on each of these cycles in time, you actually get a little bit of amplitude, and they add up in phase. Okay. So you can, in fact, then make the transition from here to here, even though on any given cycle you don't have very much amplitude. In fact, you could write this out as a phasor sum. It looks exactly like diffraction. It looks exactly like the two-level transition probabilities in Ramsey's book. And you can also see why it's a Bessel function. If you look at this picture, here are two levels in the static field. So, and I'm assuming, say, that it's at the 4-photon resonance. So the upper state comes out and does this. We get a little amplitude for transition each time. Since the phase from one cycle to the next is 8 pi, they all add constructively. Now if I raise the field, of course, now actually I can have the upper state go through this twice on each cycle. So the resonance condition means that the red ones, the red avoided crossing traversals add constructively, and the blue ones do, but it doesn't tell you anything about how the red ones add to the blue ones. In fact, the total accumulated phase over one cycle between the upper state and the lower state is actually the difference between this area and this area. And if this phi2 area, okay, when either one of these is an odd multiple of pi, then the red and blue ones cancel. And that's how you get the zeros in the Bessel function. Okay, so, so in fact, this 1/3 n to the 5th ionization is really just the overlap of these sideband states. Okay, so you could actually apply precisely the kind of analysis we've just gone through with the Bessel functions and the Landau-Zener things to dipole-dipole energy transfer in the presence of an RF or microwave field. Okay, so I would like to now actually go on to something similar to what Barry Dunning talked about. And we're going to start from our Floquet states again. So I once again have my two S&P states. These are the Floquet states. And now what I would like to do is to plot the energy of one of these pairs as a function of the applied electric field. So at resonance, these two would be right at the top of each other, but in general, they're not. Okay, so as I said earlier, the Floquet eigenstates are periodic, and the energies are cycle average energies. Okay, so this cycle average energy goes up, this cycle average energy goes down. And this is in the presence of a field that's oscillating at frequency omega. So this means then that the dipole, if I'm going to get time average energies, the dipole has to be oscillating at the same frequency. And in this case, the dipole is aligned up or opposite the field. In this case, it's aligned with it. So in short, in both of these states, the dipoles are phase locked to the field. And actually, okay. So if the dipoles are phase locked to the field, and this transition, say, is the delta n equal 1 transition, that is at the classical orbital frequency. If you chirp the frequency of this field, you should be able to speed up the orbital frequency of the atom. And so this, of course, is just a different way of doing what Barry discussed yesterday. So, for example, I should be able to move n equals 72 to 82 atoms by chirping a microwave frequency from 19 to 13 gigahertz, because this is the delta n spacing here, that's the delta n spacing there. So as I decrease the frequency, I expect the orbital frequency to go down, and the atom will get bigger. Okay. So to do that, and to see if this is actually true, you can in fact excite lithium atoms, the pulse laser to n equals 72, expose them to this chirp microwave pulse that does this in about 500 nanoseconds, and then apply a field ramp to ionize the states. So initially they're in n equals 72, and we're hoping they'll go to n equals 82. So, at low microwave power or no microwave power, you expect to see a signal here, and at higher power, you expect to see it up here for n equal 82. And these are not such beautiful data, but anyway. So when the field, so these are sweeps taken on increasing field strength, and at low field strength or no field strength, you can see that the peak is here. This is n equals 72, and at fields of about roughly a little less than a tenth of a volt per centimeter, you can in fact make the transition up to n equal 82, and you can do it over about a factor of 10 in microwave power, and then everything ionizes. Okay, so this actually works. But it's interesting to remember that the atom is a quantum mechanical object, or at least the last time I looked. And so you can actually describe this process quantum mechanically as a sequence of single photon adiabatic rapid passages. I mean, at least that's our starting point. And just to be sure so an adiabatic rapid passage is the same thing as an adiabatic traversal of a Landau-Zener avoided crossing, except that now it's the frequency that you change to, in fact, change the spacing between the levels. So the criterion is simply that the frequency sweep, or the frequency chirp, the rate at which you're changing the frequency, has to be small compared to the Rabi frequency. That's okay. So this is, of course, how you would, in fact, do adiabatic rapid passage in our simple two-level system. It's actually useful to consider how do you do this to actually chirp it through 10 levels? Because if I back up one step, if I actually had simple avoided crossings here, you wouldn't get the picture that I just described. And as you go through the transitions, the electron is phase locked to the field, but it's not between encountering the resonances. Okay, anyway, so what I'd like to do is to sort of expand this notion to let us describe changing it by 10 states.